Hi, my name is Joshua Cook, and today I'm going to talk about time and space efficient deterministic list decoding. This was joint work with Donna Moshkowitz. So first, let's review basic error correction. Error correcting code is just a function that takes any two distinct inputs to distinct outputs that disagree on a large fraction of indices. The relative distance is the fraction of indices they disagree. The rate is the length of the input divided by the length of the output. And we want a code that has as high of a relative distance and high of a rate as possible. And we say that a code is asymptotically good if the relative distance and the rate are both constant and the alphabet is also constant. The code word are just the range of the code. And we really want codes that have a distance that's very close to 1. So how do you actually use a code for decoding? Imagine you received a word. You think of it as some code word with a little bit of corruption, and you want to know that original code word. Well, since your code has distance, you know that your received word can only be close to one code word, and this lets us do unique decoding. But we can only decode up to half the decoding radius in that regime. If you want to decode more, well, sometimes you're still close to only one code word, and that works. But sometimes you'll have a word that you'll actually be corrupted by going closer to another code word. Now you can't really know whether you came from C of Y or C of X. But you can only be this close to a handful of code words. So if we're allowed to output both, then we will guarantee that we output C of X. We just also have to output C of Y. And that's what a list decoder does. A list decoder is just an algorithm for code that takes in a received word and outputs a list of guesses of what the original message was, such that any code word that's close enough to the received word will output the message from that code word. So the real question is, can we get some advantage from list decoding? And the answer is yes, if your code has large distance. So consider this word that agrees with C of X on gamma fraction, C of Y on gamma fraction, and C of Z on gamma fraction. Now let's take any other C of W here. It can agree with C of X on alpha fraction, but it can't agree on it more. And it can agree with C of Y alpha fraction, but it can't agree on it anymore. And altogether, this might not be enough for it to agree with W on gamma fraction. Two important examples of error correcting codes are the Reed-Solomon codes and the Reed-Muller codes. Reed-Solomon codes are just univariate low-degree polynomials evaluated at all points on the polynomial. Reed-Muller codes are codes whose code words are multivariate low-degree polynomials evaluated at every point. So we are going to work in the regime where we want to do a low space decoder. So we have some input that you can't change. We can query it, but we can't change it. And we have some output we can write to, but you can't read from it. And in the middle, we have small space, and we still want to do list decoding in this regime. And our main result is that, in fact, there are efficient list decoders. So for any polynomial that's arbitrarily close to linear polynomial, and any space that's an arbitrarily small polynomial, and any distance that you want to list decode from, there is an asymptotically good code that can be list decoded from that distance in that time and that space. And in fact, these are just Reed-Muller codes. We find efficient uniform list decoders for Reed-Muller codes. Now we're going to review our prior work on time and space efficiency of error correcting codes. In 2005, Bazzi and Merder showed that for any good code, any encoder for that code that runs in linear time must also use linear space. But their time-space lower bound doesn't really give anything for the space once you allow it to have quasi-linear time. Santhi and Vardy showed that encoders for self-dual codes require a time and a space such that the space times the time is at least n squared. And there are also known to be non-explicit codes, such as the repeat accumulate codes, that can be encoded in quasi-linear time and logarithmic space, but we don't know how to make these codes explicit. Later, Cook and Moshkovitz gave codes with a uniform encoder that runs in almost linear time and subpolynomial space. For decoding, Reed-Muller in 2006 proved that non-adaptive decoders for good codes that run in time t and space s must have that s times t is at least n squared. It's also known that locally correctable codes give asymptotically good codes that have a randomized decoder. But last year, we were able to give a deterministic decoder for an asymptotically good code that runs in almost linear time and subpolynomial space. Now, before we get to actually showing you how to do list decoding for Reed-Muller codes, we're going to show you a lower bound for encoding or decoding Reed-Solomon codes space efficiently. So local structure in our case is any code such that by querying a few symbols of the code word, you reveal information about another symbol of the code word. And all local properties require some sort of local structure. Locally testable codes, locally decodable codes, locally correctable codes. Basically any local thing with local in the name has this local property. And local structure in this sense for linear codes is equivalent to having a small dual distance. Now, Reed-Solomon codes are not local in the sense that if you give me any d+1 points and you assign me any values to those d+1 points, then there is a Reed-Solomon code word that goes through them. So by giving me any d points, that doesn't tell me anything about the value of any other point. And this is equivalent to saying that like random code words are d+1 wise independent. So our lower bound holds for any code such that a random code word is a d+1 wise independent distribution. And the idea is to imagine that your algorithm starts with s symbols of information, can be any s symbols of information, but has s symbols of information. Then we suppose that the algorithm reads d minus s more symbols, and then without reading any more, outputs s+1 symbols of information. If you look at this, all d+1 symbols of what is read plus what is written are possible. They're all valid in some code word, but we really only have like d symbols of information. So this extra symbol still is going to be random. We can formalize this a little bit more. There are, literally sigma to the d+1 possible assignments to the symbols read plus the symbols written. All of them are possible, but there are only sigma to the d possible combinations of your starting memory state and your symbols read. Since there are more possible assignments to these symbols than the number of combinations of symbols read and starting states we could have had, this means that there must be some valid assignment to these that has the same starting state symbol read combination. For these we must have written the same thing, but that means we must have written the wrong thing for at least one of them. So putting it together, we can get this following lower bound. For any decoder that decodes E errors in a code that's d+1 independent, that decoder must run in a time and a space such that the time times the space is at least the independence of the code times the fraction of errors you correct. And for asymptotically good codes with like no locality that's sublinear, this requires your time and your time space to be quadratic. So it takes a little bit more effort to formalize this, and a few concerns you might have is that some code words might always be fast to decode, like the all-zero code word. Yeah, you just bound the expected time of the decoder instead of like saying it always takes a long time. You just say an expectation it takes a long time. You might ask, how do we formalize that the state only has S symbols of data? Well, you just basically do a probabilistic argument with high probability whatever state you get had a large fraction of code words that reach that state. Another concern you might have that the symbols that are read or written is a function of the code word and potentially the corruption on the code word. So how do you make that argument before? Well, it's two things. One, if the decoder is deterministic and it starts at the same state and reads the same symbols, then it always reads and writes to the same locations. But more generally, the counting argument sort of just goes through either way. Doesn't matter. A couple extensions to this. This argument I stated for decoding, but it works for encoding or decoding. Non-linear codes can also have this independence property, so this doesn't just hold for linear codes. And even if your code has a few local constraints, as long as there truly are only a few local constraints, you can sort of get rid of them by fixing symbols in those constraints in sort of arbitrary, valid way. Then the results you'll get will still be a code, and it won't have any local property anymore. So it can't have an efficient decoder, and you can't have a special case, a subcode, be harder to decode than the original code. Now, one of the most important tools we're going to use in this is local correction. So let's talk about local correction for Reed-Muller codes. So Reed-Muller codes, as you may remember, are multivariate low-degree polynomials, and that means that a line through a Reed-Muller code is a Reed-Solomon code. So take this example here. The green is there it's been correct, and the red is where it's been corrupted. If we want to locally correct a point here, we're just going to take a random line to that point, and then we're going to do local correction on that Reed-Solomon code word. If you don't see much corruption, then that local correction will succeed and allow you to recover that symbol. But you can't make this deterministic. If you always check the same points, then those points could be adversarially corrupted and your local correction will not succeed. Remember, we're trying to get deterministic list decoding. A locally correctable code is just a code that has such a randomized corrector, such that for any symbol that you want in a partially corrupted code word, you can make few queries, and with high probability, you will get the symbol from the corresponding code word and not the word that you received. Now, most codes we consider are systematic, so correction basically implies decoders, and there are list decoding variants of this, which, similar to in the unique case, you got time and space efficient randomized unique decoders. This also gives time and space efficient randomized list decoders. One of the main tools we're going to use for list decoding is basically our prior tool for unique decoding. As a quick refresher, you can de-randomize local correction by running the local corrector, several times and just finding some local correction that works. But you might have to go through a linear number of local correctors first, and checking each local corrector could take linear time. So overall, the naive de-randomization for this takes quadratic time. But if you only want to decrease the fraction of errors a little bit, then you only need a smaller number of functions. And that is exactly what we did in our prior work. So we have some functions that on average decrease the fraction of corruptions. And our algorithm just looked at the functions until it found one that decreased the corruption enough. Then it fixed that function, and it looked for a function that decreased the corruption again, and so on until there are no corruptions. Since each one of these functions are local, this gives us a local overall algorithm, and as long as we choose a number of functions that is correct, by the time we get to 0 corruptions, we can still have few enough queries that this is still local, and thus it is time, space, and time efficient. Great. We now have an iterative approach to do local decoding. Let's just apply it to list decoding. So let's take a line here, and let's do local decoding, and we get multiple things out of it. But which one improves the code word? Well, they all kind of improve the code word, just in slightly different ways. So which one do we take? Well, we're going to have to use list recovery. So in list recovery, instead of receiving a single record, you receive several candidate symbols per index. So here's some candidate symbols, and you need to output all code words who have many symbols in these lists. So here's a couple of code words, and you can see that each one of them has a few symbols that are missing the list, but most of the symbols in these code words are in one of the lists. So to extend the unique correction to list correction, if most of these lists are exactly right, then the iterative correction works. And we don't need them to be exactly right. I'll clarify that in a moment. Once there are 0 errors in the list, then it's pretty easy to split them into distinct code words. What makes this tricky is that there are kind of 2 kinds of errors. Kind of encode word errors. These are symbols in a nearby code word that are not in any of the lists. But this is pretty easy to deal with by using sampling properties. Then there's out of code word errors. These are symbols in lists that are not in any of the nearby code words. So they're extra symbols in the list that shouldn't be there. And the problem of this is that when we're searching to find a function that will improve the code word, this can make false negatives. So it can make it harder to find a function that improves the code word. Sampling can rule out of code word errors as well, but we need to have a small number of out of code word errors first. The problem is that standard list correction does not bound out of code word errors at all. It's just not part of the definition of list correction. And as I said before, we can actually handle more than like half of the lists being wrong as long as there's sort of a gap between the number of in-code word and out-of-code word errors. So we can even handle a large number of out-of-code word errors as long as there's a gap between the number of out-of-code word errors and the number of in-code word errors. So to overcome this problem, we're going to use codes that have local testing properties. And we're going to use a variation that's like list local testing. So in the standard local testing, you received some words. So the cyan is one code word, the green is another one. And you check a few spots and you're trying to say, did what I see look like a code word? And that's great. But then whenever you check something and you see 2 different code words, you go, not a code word. But that's a problem because in the list decoding world, you're not close to one code word. You might be close to multiple code words. So I can't just reject this view outright because we kind of expect this to happen a lot. But instead, we can say that it looks like it's only green and cyan code words. There aren't any like red code words. And that's what I mean sort of like a list testing version of it. So let's take this example where we have a green code word here and a blue code word over here, and we look at it locally, and you might say it looks kind of like a green, cyan, and blue code words, because cyan is like a mixture of blue and green. But that's bad. We want to very rarely output a third code word that is not one of the 2 code words that we're interested in. Different codes will share some local views, but any 2 specific code words will share very few local views. That's how the local views correspond to the code words. So the particular properties we need from the local testers is that they need to be randomness efficient, because this needs to be time and space efficient to look through all of the local tests. It needs to work in the high error setting, so it needs to have that lists decoding properties we were just talking about. And we need the local tests to also be a local correction. And Moshkovitz and Raz gave a low degree test for the Reed-Muller codes that satisfies all 3 of these properties. We will give a local tester just for Reed-Muller codes, and our local testers are just going to be a set of subspaces. And these subspaces need the property that for any word that you receive, if you give me some low-degree polynomials for each one of the subspaces, and all of these low-degree polynomials do not agree with one of the nearby code words, then in expectation, the low-degree polynomials you gave me are not going to agree with the received word. So some of the local low-degree polynomials may match the received word exactly, but in expectation, not many of them will. And that's the local list testing type property that we will actually need. The local list tester that Moshkovitz and Raz gave was this efficient plain versus point test. So in this test, you take a uniformly random point, then you choose 2 directions, but not uniformly random. You choose them using a subfield of whatever field your space is over. and then you check the plane that goes through this point. These planes are going to be the subspaces in the previous definition. Okay, great. So, can we just decode using these planes? Well, unfortunately, subspaces, including planes, are not good enough samplers to do the iterative decoding process that we used in unique decoding. But we only need the local testing to work in the first round to get the number of errors low enough. After the out-of-code word errors are small, then we can just use sampling arguments, and the prior work gave us sets of lines that are good enough samplers for those arguments to work. Now, how do we choose some choice of these planes for these first round? We don't. We actually didn't figure out a way to do this, but there's not that many of them. It's randomness efficient, so we're just going to brute force and try some random directions, do the local correction, and see if this ends up list decoding. If it doesn't, we'll try the next one, and we can just brute force all of these. It's fine. And that's our main result, but now to talk about some open problems. Our first open problem is to find a single code that is both encodable and decodable in small time and space. So our prior results gave a code that's encodable time and space efficiently, and this work gives a single code that's list decodable time and space efficiently, but it's not the same code. We would like to have one code that you can do both. Another limitation of this work is that our constants are outrageously large, and this is mostly due to limitations on our list local testing algorithm. It has very large constants. So if you can improve the local testing algorithm, then you can give better constants for our local list decoding algorithm. It'd also just be good to give time and space efficient uniform decoders for more codes, like multiplicity codes, for instance, or lifted Reed-Solomon codes. In this work, we only gave list decoders for Reed-Muller codes. It'd be nice to have it for more. Finally, Reed-Muller codes are not asymptotically good in the regime where you use a subpolynomial number of queries, and this means that we can't get true subpolynomial space, almost linear time list decoders for good codes. It'd be nice to get that result.